and welcome to students. Now today's lectures we are going to discuss the topic chemical kinetics. In this topic now we are going to learn the second order rate equation. You know that the rate of second order reaction can influence by the concentration of the two reactants. The last lectures we have seen the rate equation of first order reaction having the one reactors are converted to the products. But in second order reactions, it is the two reactants having the two same reactants or two different reactants can react and to give different products or corresponding products. Such two molecules, it may be same reactants or may be different. So such are two different types of second order reaction. It is first the two reactants with having the similar gives products. So rate of such reactions is equal to this K is equal to this concentration of A to 2. And other type rate of reactions having the two different reactors can react and to give the products, and therefore rate of the reactions is equal to this K into the concentration of A into concentration of B. Now such a types of this is a second type of reactions having two possibilities. One possibility is that the equal initial concentration of the two reactants, right? Equal initial concentration of the two reactants. It means that such two reactants, they will have the same concentrations, or these two reactants having the same concentrations, and other fact they will having a different concentrations or unequal concentrations. It means this is the equal initial concentration of the two reactants like A is equal to B, but unequal concentrations of the two reactants having A is not equal to the B, where the small a and small b will they represent the initial concentrations of the two reactants like capital A and capital B. The integrate rate equation for second order reactions with equal concentrations we are learned in this topic. Let's this A is the mole per dm cube, is the initial concentrations of the each reactants capital A and capital B at the state of the reaction, and X will be the mole per dm cube of reactants capital A and capital B reacts up to time t. And therefore the concentrations of each of the reactants capital A and capital B at time t will be A minus X mole per dm cube. But at a time t, the rate of the reactions will be given by as like rate is equal to dx by dt is equal to the rate of reaction K into A minus X square. So this equation are the differential equation for the second order reactions with equal concentrations of the two reactants. On rearrange those equations, we get like dx upon this is A minus X bracket square is equal to K into this dt, cross multiplication, K into dt. Then this equation now integrate between the limits, that is t is equal to 0 and x will be 0 since no reaction has occurred at time t is equal to t and x is equal to x. Now integration of those equations, that is limit x is equal to 0 to x is equal to x into dx upon a minus x bracket square is equal to k into integration t equal to 0 to t equal to t into dt. By solving those integration, get 1 upon a minus x minus 1 upon a minus 0 is equal to k into t minus 0. By solving those equations, then 1 upon a minus x minus 1 upon a minus 0 as a is equal to this k into t, so kt, a into t minus 0 is equal to t, right, t. So by solving those, then this is cross multiplications like this, a minus into a minus x upon this multiplication a into a minus x is equal to kt. Then this x upon a into a minus x is equal to the kt, that is this a and this a, they will be cancelled, that is minus minus get plus, so a will be cancelled, so x upon a into a minus x is equal to kt. Hence those equation can rewrite like k is equal to, this is k is equal to this x upon a into a minus x is equal to kt, and therefore k is equal to, so this t is here is a into, is going to this side is a denominator, so this is k is equal to 1 upon, this is a t into x upon a minus x, equation 2. So those equations second is the integrated equation for the second order reactions having the equal initial concentrations of the two reactants. So this is called as the rate equation for the second order reactions. Now we have some characteristics for the second order reaction. First, you know that the second order rate equation k is equal to 1 upon a into t into x upon a minus x. Now we have the unit of second order reactions. So those terms, that is the x upon a minus x, these terms will be a number, and therefore this equation can rewrite as like k is equal to 1 upon at into number, and hence the unit of this rate order rate equation is equal to per time, right, per concentration. A is the initial concentration, T is the time, so per time per concentrations, and therefore 1 upon concentration can measure mole per dm cube into temperature, time in second. So equation can be write is here like dm cube is minus will be convert to plus. So dm cube mole convert to per mole. So dm cube per mole per second. Dm cube per mole per second. This is the unit for the second order reaction. Further, this K is directly proportional to 1 upon A. The value of K, they will be inversely proportional to the initial concentration of the reactants. Now we have going to discuss half-life period for the second order reaction. The rate equation for the second order reaction is K is equal to 1 upon AT into X upon A minus X. When 50% the reactant can convert to product as like the X is equal to A by 2. Putting these values of this X, and therefore equation can becomes K is equal to 1 upon A into T half 1 into T half into A by 2 upon A into A minus A by 2. For those calculations, 2 into A twice A minus A, so A by 2, right? So A by 2 is here. And you know that T half is equal to 1 upon A into K. So A by 2, they will be cancelled, are here. And therefore, this T half for this we can calculations. So 2 into twice A minus A, so A by 2. This A by 2 and A by 2 will be cancelled, are here. Then remaining term is this. So K is equal to 1 upon A into T half. By cross multiplications, that is K is here and T half is there. So T half is equal to 1 upon A into K. So T half is equal to 1 upon A into K, or T half is directly proportional to, T half is inversely proportional to A. According to the second order rate equation, the time for half reaction is inversely proportional to the initial concentrations of the reactants. And this characteristics can be used to determine whether reactions belongs to second order or did not. Can be explained from those equations which are used for the such characteristics to determine second order reactions. Next characteristics we have see are here graphical representations of second order rate equations. Now consider the second order rate equations is like K is equal to 1 upon AT into X upon A minus X, or this modify those equations, then X upon A minus X is equal to K into A into T. Then those equations can write in the form of y is equal to mx, and hence the plot of this x upon a minus x against t. Plot of x upon a minus x against t. Ka is the slope, and slope is the Ka. So passing, so straight line which is obtained, which is passing through the origin with the slope Ka, or K is equal to the slope upon A. Hence, the rate constant can be calculated from the slope of the plot, which is shown is here, like this: x upon A minus x versus time, to obtain the straight line which is passing through this origin, and Ka is the slope. Therefore, slope is equal to Ka, or K is equal to the slope upon A. Or the second order rate equation can be rearranged for those equations as like the Kt is equal to 1 upon A into x upon A minus x. So this 1 upon A minus x minus 1 by A is equal to K into T. So those equations we can rearrange in the form of y is equal to mx plus c. And therefore, plot of this 1 upon A minus x versus time, they will be also straight line. They also straight line with the slope equal to k, with slope equal to k, having the intercept equal to, this is the intercept equal to 1 upon A, this graph. So 1 upon A minus x is equal to k into t plus 1 upon A is a constant having the slope, right? So from the graph 1 upon A minus x versus this t, which obtain the slope as the rate of the reactions, and having the slope is a 1 by A. And now next points we are going to learn some examples for the second order reactions, as like the first examples we see is here: decomposition of hydrogen iodide. The two molecules of hydrogen iodide can decompose as hydrogen gas plus I2. Similarly, the two molecules, one molecule of H2, one molecule of I2, reduce twice HI. Some mistake is there in the print mistake, so we can change this there like this. So it is twice H and I, right? Twice HI. Okay. Then next examples, the decomposition of ozones. So two molecules of the ozone can decompose and produce thrice O2 gas molecule. Similarly, other examples, the two molecules can react having, this is a one molecules of methyl acetate, second molecules of NaOH. So two molecules can react and get methyl acetate, right? This is also some more problems are here. So now we have write this product as like the CH3, then CO, right? Then young A, sodium acetate plus the ethyl alcohol, right? C2 HO, C2H5OH. So ethyl alcohol is the product. Similarly, other reactions like two molecules, one molecule of nitrogen gas, other molecules of oxygen gas to produce twice nitrous oxide gas. Similarly, other reaction, esterification reactions, that is methyl acetic acids, one molecule, second molecule ethyl acetic acid can react and to get produce the methyl acetate. So this is some more examples for the second order reaction.